Okay, so welcome back to this next video in which we are discussing the opioid receptors. Okay, so we are looking at the downstream pathway for opioid receptors, and we've discussed that they activate heterotrimeric G proteins of the GI form, which means that the alpha subunit of the heterotrimeric G protein is an alpha I form. So it's either alpha I1, alpha I2, or alpha I3. Okay, then you produce these two separate subunits. You produce an alpha I GTP subunit, and you also produce a beta gamma subunit. Okay, and these can then go on to activate certain targets. Okay, so we're in the process of discussing, regulate certain targets rather than activate certain targets, because actually we're going to see inhibition in this case. Okay, they can go on to interact with certain targets. Okay, so we're discussing the alpha I GTP subunit and its effects on adenylyl cyclase enzymes. So we've discussed the structure of adenylyl cyclase enzymes and how they're activated by the dimerization of the C1a and C2a domains. Okay, we're now in the process of discussing the 9 different forms of adenylyl cyclase enzymes and how they are categorized. Okay, so let me get another piece of paper and we'll discuss this. Okay, right. So, basically, adenylyl cyclases are grouped into 4 different groups. So, we'll start with group 1 then. Group 1 is also called the calcium-activated adenylyl cyclases, and it contains adenylyl cyclase enzymes which will be activated by an increased concentration of calcium in the cytoplasm nearby them. Okay, so this group includes adenylyl cyclase 1, adenylyl cyclase 3, and adenylyl cyclase 8. Okay, so 3 members of the 9 that are in this group 1 calcium-activated adenylyl cyclases. Next group is group 2, which is again another group of 3 adenylyl cyclases, and its sort of colloquial name is beta-gamma activated. Okay, so these can actually be activated by the beta-gamma subunit, but only if the adenylyl cyclase has already been activated by an alpha S subunit. Okay, so actually the beta-gamma subunit can't actually activate adenylyl cyclases on its own. It can only potentiate the activation that has already been produced by a G-alpha S subunit. Okay. So, the adenylyl cyclases which are in group 2 are adenylyl cyclase 2, adenylyl cyclase 4, and also adenylyl cyclase 7. Okay, next up we've got group 3, which is going to be very important for us, and this is the family of GI/calcium inhibited. Okay, so this family of adenylyl cyclases are not only inhibited by the alpha I subunit of the heterotrimeric GI protein, but also by calcium. So they're the exact opposite of group 1, basically. They're actually inhibited by intracellular calcium. And this contains adenylyl cyclase 5 and also adenylyl cyclase 6. Okay, then next up we've got group 4 adenylyl cyclases, and there's only one that can possibly be in this, okay, and this, its sort of colloquial name, is the forskolin insensitive adenylyl cyclases. So basically most adenylyl cyclases will be activated by the drug forskolin. Okay, so it turns the inactive adenylyl cyclase into the active adenylyl cyclase. But adenylyl cyclase 9 is forskolin insensitive, so it will not be activated by exposure to this drug forskolin. Okay, right. So that's the classification of the 9 forms of adenylyl cyclases. Okay, so we're going to see how the alpha I GTP subunit can interact with these 3 and also these 2 here. Now, it's obvious that it can interact with these 2 because the name of their group tells us that. It's less obvious that it can interact with these 3. Okay, so we'll actually begin with group 1 because it's the more complicated one. So let's save the best one, the easiest one, till last. Okay, so group 1 basically the alpha I GTP subunit can bind to group 1 adenylyl cyclases. However, it does not cause inhibition of them, okay? Instead, it blocks the activation of them by calcium. So remember, the special thing about group 1 adenylyl cyclases was that they were activated by calcium, okay? So if calcium goes up in the cytoplasm nearby the adenylyl cyclase enzyme that's in this group, it will cause activation. Okay. However, if the adenylyl cyclase has an alpha I GTP subunit bound to it, then even if the calcium goes up in the cytoplasm nearby it, it will not cause activation of that adenylyl cyclase enzyme. Okay, right. So, firstly, I just want to discuss what is known about the activation of calcium by the activation by calcium of adenylyl cyclase 1 and 8, because they have quite interesting mechanisms by which calcium can activate them. So let's start off with adenylyl cyclase 8. Okay, so I'll draw adenylyl cyclase 8 here. So here is transmembrane domain 1, here is the C1 domain, here is transmembrane domain 2, here is the C-terminal tail, okay, and the carboxylic acid right at the end, and the amino terminus up here. Okay, so basically what happens is when calcium goes up, it's going to activate this adenylyl cyclase 8. However, how does the adenylyl cyclase 8 actually sense that calcium has gone up? Does it have a binding site for calcium? Well, the answer is no. Instead, what it does is it binds to the protein calmodulin, and calmodulin then has a binding site for calcium. So let's discuss calmodulin. Okay, so basically, apocalmodulin means calmodulin when it has no calcium bound to it. So let me show you the structure of apocalmodulin. So apocalmodulin has this two-lobed structure. Okay, so it has these two lobes, the N lobe and the C lobe. Okay, and basically both of these lobes have calcium binding sites. So each of the N lobe and the C lobe has two calcium binding sites. Okay, so 2 on the N lobe and 2 on the C lobe. And then between these two lobes, you then have a linker region, okay, and this is at the moment is a linear polypeptide. Now you will notice that the overall structure of apocalmodulin looks kind of like bent over, basically. It's as though the two subunits have been bent back towards one another. Sorry, the two lobes have been bent back towards one another. Okay, so this is the structure of apocalmodulin. A linear polypeptide connects the two lobes, and the two lobes are sort of bent back towards one another. Okay, what happens is when calcium binds to these 4 calcium binding sites on the apocalmodulin molecule, it causes a conformational change. And firstly, the two lobes sort of spring out. Okay, so they move further apart from one another. And then also the linker between the two lobes goes from being a linear polypeptide to being an alpha helix. Okay, like so. Okay, so this is the calcium bound form. Okay, so I'll show the calcium as green dots then. So you have a green dot here, a green dot here, a green dot here, and a green dot here. So 4 calcium ions overall need to bind to the apocalmodulin to turn it into a calcium calmodulin complex. And I haven't actually told you that. Yet this new form of calmodulin, when it has calcium bound to it, is called the calcium calmodulin complex. Okay, right. Now, I also want to tell you about the abbreviations for apocalmodulin and calcium calmodulin complexes. So basically, apocalmodulin is usually abbreviated to apo, and then calmodulin is usually abbreviated to uppercase C, lowercase a, uppercase n, apocam. And calcium calmodulin complexes are then usually abbreviated to Ca2+ for calcium, and then calmodulin, uppercase C, lowercase a, uppercase m. So calcium cam is a calcium calmodulin complex. Okay, so basically, calmodulin changes conformation in response to calcium binding to its 4 calcium binding sites. So, how does this all relate back to adenylyl cyclase 8? Well, basically, in the inactive form of adenylyl cyclase 8, where there is no calcium around, basically there is a special domain on the amino terminus over here, which is known as the calmodulin recruitment domain. Okay, so this is called the calmodulin recruitment domain. Okay, and I will colour that in red. Okay, and basically this site is capable of binding to apocalmodulin. Okay, so in will come a molecule of apocalmodulin here, and that will sit on the calmodulin recruitment domain until calcium goes up. Okay, so when calcium goes up in the vicinity of adenylyl cyclase 8, the calcium will bind to the 4 calcium binding sites that the apocalmodulin molecule has, converting it into a calcium calmodulin complex, and that calcium calmodulin complex is then moved from the calmodulin recruitment domain onto the C2b domain. Okay, so remember, the C1 domain is this loop between transmembrane domain 1 and transmembrane domain 2, and is split into C1a and C1b. The C2 domain is this portion of the C-terminal tail here, where you have C2a and then C2b. So basically what happens is you have apocalmodulin bound to the calmodulin recruitment domain when there is low calcium around, and then what will happen is when calcium goes up, calcium will bind to the 4 binding sites of the apocalmodulin, converting it into a calcium calmodulin complex, and this will then be transferred from the calmodulin recruitment domain onto the C2b domain. So it moves from there onto there, and then the calcium calmodulin complex on this C2b domain then promotes the dimerization of the C1a domain with the C2a domain to produce an active adenylyl cyclase enzyme. Okay, so that's how calcium basically causes the activation of adenylyl cyclase 8. It's slightly different in the case of adenylyl cyclase 1. In the case of adenylyl cyclase 1, the apocalmodulin, instead of binding to the special calmodulin recruitment domain on the amino terminal domain here, instead the apocalmodulin binds to the C1b domain here, and then when calcium goes up in the vicinity of the adenylyl cyclase 1 enzyme, that apocalmodulin will receive 4 calcium ions binding to it, and it will convert into a calcium calmodulin complex, and then the calcium calmodulin complex doesn't swap sites in the way that it does in the case of adenylyl cyclase 8. It stays on the C1b domain and then promotes the dimerization of C1a with C2a to produce an active adenylyl cyclase, which will then convert ATP into cyclic AMP and pyrophosphate. Okay, so that's how calcium activates adenylyl cyclase 1 and adenylyl cyclase 8. Now, we're not going to look at the mechanism by which calcium activates adenylyl cyclase 3, but it also activates adenylyl cyclase 3. So, basically, what happens is the alpha I GTP subunit will bind to adenylyl cyclase 1, adenylyl cyclase 3, and adenylyl cyclase 8. So let's show this. So here is transmembrane domain 1, here's the C1 domain, here is transmembrane domain 2, and here is the carboxylic acid tail here. Okay, and then what's going to happen is the alpha subunit of the GI heterotrimeric G protein will come and bind here. Okay, so this is alpha I, it's got GTP bound to it. This will come and bind here, and basically it will stop calcium from being able to activate this adenylyl cyclase. Okay, whether it's adenylyl cyclase 1, 3, or 8. So it does not inhibit the adenylyl cyclase. Instead, it blocks the activation of the adenylyl cyclase by calcium, and there is a subtle difference in that. Okay, now that is for adenylyl cyclase 1, 3, and 8. Okay, but the G alpha I GTP complex also has effects on adenylyl cyclase 5 and adenylyl cyclase 6. And in this case, it's more simple. Okay, in this case, the alpha I GTP subunit will just bind to the adenylyl cyclase 5 and the adenylyl cyclase 6 and will actually just inhibit the enzyme, i.e. reduce its ability to activate and produce cyclic AMP from ATP. Okay, so basically, overall then, these alpha I GTP subunits will inhibit adenylyl cyclase 5 and adenylyl cyclase 6, and it will stop the activation of the adenylyl cyclase 1, 3, and 8. Okay, so the point to stress is that these alpha I GTP subunits don't have effects on absolutely every single adenylyl cyclase, but they do have effects on a good majority of them. Contrast that to the alpha S subunits, or the alpha OLF subunits, which remember are very similar to the alpha S subunit, which actually activate all 9 forms of adenylyl cyclase. Okay, so alpha S has a greater number of adenylyl cyclases which it interacts with compared to alpha I. Okay, so in the next video what we'll do is turn our attention away from the alpha subunit of the heterotrimeric G protein and towards the beta-gamma subunit of the heterotrimeric G protein.